So now let's look at proving an intersection. So I want us to prove that the intersection from n equals 1 to infinity, 0, 1 plus 1 over n, is the interval 0 to 1. So remember, you're showing two sets are equal. There are two parts to the proof. So let's prove that the intersection is contained in the interval. So how would this proof start out? What would the start of this proof be? You're going to let x be in the intersection 0, 1 plus 1 over n. And then what do I need to get to? I need to conclude that x is in this interval right here. So my end will be that x is in the interval 0 to 1. So what does it mean to be in that interval? It means x needs to be bigger than 0, and it needs to be less than or equal to 1. So let's go back to our start, right? And I know for every positive integer, x is going to be in this interval 0, 1 plus 1 over n. If it's in the intersection, it's in every one of those sets. So what does it mean to be in this interval right here? It means, so for all n and z plus, x is greater than 0 and x is less than 1 plus 1 over n. So here I've already got half of what I need. I have x is bigger than 0. And so now let's look at this other part that I have right here. Okay. So let's see, this is true for every value of n. So let's see, if I plug in n equals 1, right, I would say x is less than 2. If I plug in n equals 2, it would be x is less than 3/2. But these numbers are all too big to get to my conclusion. Here, I need to say that x is less than or equal to 1, and these numbers are too big. So I can't really get from, so to get from here to here, I can't actually do that. So what this means is that proving this directly has failed. So I'll sum it up and say that the direct proof fails. So what do you do when you can't prove something directly? You go to an indirect proof. So you can either use contrapositive and prove this, or contradiction. So here I'm going to use contrapositive. So remember what statement we're trying to prove right now. We're trying to show if x is in the intersection, then x would be in the interval from 0 to 1. So now what we want to do is we want to write the contrapositive of this statement. The contrapositive, remember you flip them and negate them. X is not in 0 to 1, and x is not in the intersection of these intervals. So let us go ahead and outline this proof. What would the outline look like? I'm going to start with x is not in this interval 0 to 1. So what does it mean to not be in that interval? Well, either it's smaller than 0, less than or equal to 0, or, oh, I'm kind of jumping the gun here. Before we do this, let's write down our conclusion. What do I need to conclude the end of my proof? I'm going to try and leave myself enough room here. The end, I need to show x is not in the intersection. So remember that this intersection is a for all statement. X is in this interval 0, 1 plus 1 over n. And because x is not in it, we want to negate this statement. So what happens when you negate a for all? It becomes there exists. So there exists an n in z plus and the positive integers so that x is not in that interval. There has to be one of those intervals that x is not in, and I'm going to call that n. So again, what does it mean to not be in that interval? It means either x is less than or equal to 0, or x is greater than or equal to 1 plus 1 over n. All right, so I need to get one of those two things happening. So let's go back up to the start of our proof. If x is not in 0 to 1, that means x is less than or equal to 0, or it's bigger than 1. Well, remember I needed to get one of two things happening, and I've already got one of those. So because this is a or statement, you're going to have to split this up into cases. So your two cases are going to be here and here. In the first case, if x is less than or equal to 0, I got one of the two things I needed to get. I needed to get x was less than or equal to 0, or it was greater than or equal to 1 plus 1 over n. Well, I got that it was less than or equal to 0. So that first case is done. So now let's look at our second case, the second thing I underlined here. If x is greater than 1, then x minus 1 would be bigger than 0. Just subtract 1. So what is this telling me? This is telling me that x minus 1 is positive. Well then, 1 over x minus 1 is also positive. So we're going to use our Archimedean principle. So I'm just going to abbreviate because I don't have a ton of room here. AP, by the Archimedean principle. There exists an n in z plus. We're using that corollary where n is bigger than 1 over x minus 1. So here n is positive and x minus 1 is positive. So what I'm going to do is I'm going to work with this inequality a little bit. I'm going to divide by n and multiply x minus 1, and I don't have to worry about the sign flipping because everything is positive. X minus 1 is bigger than 1 over n. And so if I add 1 to this inequality, x is greater than 1 plus 1 over n. And that's exactly what I needed to get down to. I needed to be able to say that either that x was greater than or equal to 1 plus 1 over n. Well, I said it was greater than. So that works. So again, now that I've sketched this part out, you could write this proof formally. But we have completed our proof from start to finish.